Hi, this is Mrs. Baisden, and this is the Aqueous ionic equilibrium calculation review. So we're going to go through each section, and we will start by talking through how to do the calculation, and then we'll do an example calculation for each different type. The first type of calculation we're going to look at is calculations that involve buffers. So one of the things you might be asked to do is to calculate the initial pH of a buffer. So the easiest way to do that is to use the Henderson-Hasselbalch equation. So to use the Henderson-Hasselbalch equation, you need the pKa of the weak acid, or the weak base that you're using, and you're going to add the log of the concentration of base divided by the concentration of acid. So here's an example of one of these. So this problem says, what is the pH of a buffer solution that contains 0.20 molar formic acid and 0.10 molar sodium formate? So like I said a minute ago, we're going to use Henderson-Hasselbalch. So pH equals pKa plus log base over acid. So the other thing that would be given here would be the Ka. And the Ka for formic acid is 1.8 times 10 to the negative 4. So you would either have to be given that or you would have to look it up as you were working this problem. So I want to know the pH of the buffer. So the pKa is going to be the negative log of the Ka, so the negative log of 1.8 times 10 to the negative 4 plus the log of the concentration of base over the concentration of acid. So in this case, sodium formate is my conjugate base. So log of 0.1 molar over the concentration of acid, in this case formic acid, is 0.20 molar. So then when I do that calculation, this ends up being 3.74 plus log of 0.10 or 0.20. So my pH for this particular buffer starts out at 3.44. So the other thing you might be asked to do with a buffer is to determine how much of different reagents you would need to prepare a buffer solution with a certain pH. So when you're doing this, the first thing you have to do is usually you're going to be given a list that kind of narrows down what your options are in terms of picking reagents. So you're going to pick the acid and conjugate base pair or the base conjugate acid pair from the list that's given that has the pKa closest to the desired pH of the buffer. And these are usually weak acid conjugate base, weak base conjugate acid. Then you're going to figure out how much of each reagent is needed using the Henderson-Hasselbalch equation. So here's an example for this one. So this one says prepare 100 milliliters of a buffer with a pH of 4.20, and then you have the following reagents available. So I have formic acid, lactic acid, benzoic acid, and then I have sodium benzoate, sodium formate, and sodium lactate. So as I'm looking at this, the first thing I have to do is I'm going to figure out the pKa of each of these acids that I have available. What that will do then is allow me to pick the acid, then I can know which conjugate base to pick to go with it. So the pKa for formic is 3.74, and again the pKa is just the negative log of the Ka, and the Ka for each one of these is given. The pKa for lactic is 3.85, and the pKa for benzoic is 4.19. So the one that I would pick would be benzoic acid, because that has a pKa that's closest to the pH of the buffer that I want to make. So this would be my acid, and then I'm going to pick a conjugate base from this column. So I'm going to pick the one that has benzoate in it. So then I would pick the sodium benzoate as my conjugate base. So then I can use the Henderson-Hasselbalch equation. So pKa plus log base over acid. But this time, instead of solving for the pH, I'm actually going to be solving for the concentration of base. Okay, and we'll look at why. So the pH I know. The pH, my target pH is 4.20. The pKa I already figured out, 4.19, plus log, I need the concentration of base, so I need to know the concentration of sodium benzoate, and then it already told me that I'm using 0.1 molar benzoic acid, so I already know my concentration of acid, so that can go on the bottom. So then I have to solve for the concentration of base. So I'm going to subtract the 4.19 from both sides, so I end up with 0.01. And then to solve for base, I'm going to change this to log base minus log acid, or log 0.1. And then when I solve for that, my concentration of base is equal to 0.10 molar. So now I know concentration of acid from up here, concentration of base, but if I'm actually going to make this in the lab, the sodium benzoate is a solid. So I have to actually figure out how many grams of that sodium benzoate I need. So up here it tells me I want to make 100 milliliters of this buffer. So I can convert this molarity of base into grams so I know how much to dissolve into my weak acid solution. So I'm going to make 100 milliliters of buffer. I'm going to change that to liters. I'm going to make a 0.1 mole base solution, or I need a 0.1 mole base solution. And the sodium benzoate, the molar mass for this, is 144 grams. So I'm going to use that down here to solve for grams of sodium benzoate. So then my final answer here, if it's saying how would I prepare this, I would need 1.44 grams of sodium benzoate, so NaC7H5O2, in or diluted to 100 milliliters of 0.1 molar benzoic acid solution. So I would use my volumetric flask, I would put a little bit of this acid in the bottom, I would add my 1.44 grams of sodium benzoate, and then fill it to the etched line with the benzoic acid to make my 100 milliliters. Okay, another calculation you could have to do with buffers is to figure out how the pH changes in a buffer solution. So when you're doing this, the first thing you have to do is figure out whether the addition will react with the acid or the base component of a buffer. So if you're adding, it depends on whether you're adding strong acid or strong base, and you have to look at which piece of the buffer that addition is going to react with. You're going to write out the equation and set up your BCA table. So don't forget, for a BCA table, the substances have to be in moles when you're using the BCA table. It's different than an ice table. Then you're going to calculate the changes in concentration, change those quantities back to molarity, and then use your Henderson-Hasselbalch equation to calculate the new pH. So for this particular buffer solution, we have formic acid and sodium formate. So this is actually the same buffer solution we calculated the initial pH of a couple examples ago. So when you have a buffer solution, I feel the easiest way to figure out what's going to react when you add an acid or base is to start by setting up the equilibrium expression that shows how that weak acid dissociates. So if I have formic acid in solution, you're going to get a little H plus and some CHO2 minus. Now if that's your buffer solution, this is your acid component of your buffer. This is your base component of your buffer. So when you add an acid to this buffer system, the acid that you add is going to be used up by the base component of your buffer. If you add a base, it's going to be used up by the acid component of your buffer. So that's important to figure out when you start, because that's how you're going to set up your BCA table. So for this one, I'm adding 0.01 moles of sodium hydroxide. So the first thing I have to do is figure out what part of that buffer this added base is going to react with. The other thing I have to remember is that a BCA table, I always use moles. So I have to change, if it's not in moles already, I have to change it back to moles. Okay, so to set up my BCA table, I'm adding OH minus. So since this is base, I'm adding base, it's going to react with the acid component of the buffer. So I'm going to start my BCA table equation with the HCHO2. Then I'm going to add the OH minus, and then what that's going to give me on the other side is CHO2 minus and H2O. So the OH minus is going to react with the H, which will generate water, and then it will also generate CHO2 minus. So when I put these values in, what I have to figure out is how many moles of each of these I have before they mix together. So I know I have 0.2 molar formic acid, but I can't put it into the BCA table in molarity. I have to change it to moles. So to do that, I have 1.5 liters of buffer, and my formic acid concentration is 0.2 moles per liter. So that means I have 0.3 moles of formic acid in this buffer. So that's what goes right here. So 0.30 moles of formic acid. It tells me I'm adding 0.01 moles of OH minus, and then I have 1.5 liters of 0.1 molar sodium formate, which is 0.15 moles. So that's going to go here. So this is everything that's in there before the reaction starts. Then when I'm looking at what to subtract, you're going to subtract the value that has the smallest amount. So the OH minus is the smallest amount, so that's going to get used up. So I'm going to subtract it from the left, and then I'm going to add it to the right. 0.29 moles of formic acid. All the OH minus gets used up, and 0.16 moles of the formate. Now before I can calculate a new pH, I have to divide by the volume to get it back to molarity. So for the formic acid, the concentration is 0.19 molar, and then for the formate, or the conjugate base, it's 0.11 molar. So then once I've done that, now I can go back to the Henderson-Hasselbalch. So the pH equals the pKa, which we figured out before was 3.74. This is the same weak acid we were using a minute ago, plus log base, which is this right here, over log acid, 0.19. So when I calculate that, the new pH after the addition of a little bit of base is 3.50. Okay, now we're going to do something very similar, except this time we're adding acid to the buffer. So we still have our BCA table. It still has to be in moles, and we're still going to use the formic acid equilibrium system. So this time, just as a reminder here, this was our acid component of the buffer, this was my base component of the buffer. So now I'm adding acid. So the acid, or the H+, is going to react with the base component of the buffer. So I'm going to start my BCA table with the base component, add the H+, which is going to give me HCHO2 minus. So I'm going to set it up the same way I did the other one. So I still have to figure out how many moles of formic and how many moles of sodium formate. So again, the way we did that before was we had 1.5 liters of buffer, and it was 0.2 molar formic acid, which gave me 0.3 moles, and then it was 1.5 liters of 0.1 molar sodium formate, which was 0.15 moles. So that's where those initial values come from. So this was 0.15, this was 0.3. I'm adding 0.01 moles of H plus, and then I'm going to do my change column. So I'm going to subtract the smallest value, which is the H plus. So subtract that from the left, add it to the right. So I end up with 0.14 moles of formate. All the H plus gets used up, and 0.31 moles of formic acid. Now before I can use the Henderson-Hasselbalch, I have to refigure or recalculate the molarity of both of these. So these are both in a 1.5 liter solution. So the molarity of formate is 0.09, and the molarity of the formic acid is 0.21. So then Henderson-Hasselbalch, pKa is still the same because we're still using the formic acid. Log base over acid, the formate is my conjugate base, the formic acid is my acid, so my pH would be 3.37. The next thing we're going to look at are titrations. So we're going to start with strong acid, strong base titrations. So anytime you're doing these problems, if it doesn't say buffer and you're asked to calculate a new pH or you're calculating a volume or molarity, you always want to identify what type of acid and base you're dealing with because the method is different when you're calculating the pH change. So if you have a strong acid and a strong base and you're asked to calculate a pH change during the titration, you're going to use a BCA table to find moles of H plus and OH minus after the addition. So when you're setting up the BCA table, the equation for strong acid, strong base is going to be H plus OH minus yields H2O. And that's because you're dealing with a strong acid and strong base, which both completely dissociate. Then you're going to convert to molarity by dividing the moles by the new volume. Then you're going to use the concentrations of H plus or OH minus to find the new pH. So we'll look at some examples for that. So this one says I have 25 milliliters of 0.1 molar KOH, and it's titrated with 0.1 molar HNO3. What is the pH after 24.90 milliliters of nitric acid has been added? So when I look at this, I would first identify what kind of a titration it is. So KOH is a strong base, HNO3 is a strong acid. So when I set up the BCA table, just like always, has to be in moles. And I'm going to use the H plus from the acid, the OH minus from the base, and that's going to produce water. Okay, so the water is not going to affect the concentration, so I'm going to cross those out. And then I'm going to use the method I used before to figure out moles of each substance in that solution. So I have 0.025 liters of 0.1 mole per liter KOH, which gives me 0.0025 moles of KOH, which is my OH minus. And then I have 0.02490 liters of HCl, which is also 0.1 mole per liter, which gives me 0.00249 moles of H plus. So then those values go into the BCA table. So the H plus was 0.00249, the OH minus 0.0025, and I'm going to subtract the one that is smaller. So I have a smaller amount of H plus, so that's what gets used up. So 0 H plus left, 0.00001 mole of OH minus left. Now before I can calculate a pH, I have to figure out what the actual concentration is, because right now this 0.00001 is moles. So to figure out what I'm going to divide by, I'm going to add my volumes together. So I had 25 milliliters and 24.9 milliliters, which is 0.0499 liters. So that then gives me a concentration of 2 times 10 to the negative 4th OH minus. So then from there, use your pH equations to figure out the pH, which in this case ends up being 10.30. So be careful with the OH minus because you'll have that extra step. So if you take the negative log of the OH minus, don't forget to then subtract it from 14 before your final pH is listed. Okay, the next thing you might be asked to do with the titration is to calculate the volume needed to reach the equivalence point. So when you're doing these types of equations, you're going to use solution stoichiometry. You're going to write out the balance equation to figure out the ratio of acid to base. And when you're setting these up, you always start with the volume of the substance that you have more information about. So here's an example for this one. It says I have 25 milliliter sample of 0.1 molar KOH is titrated with 0.1 molar HNO3. How many milliliters are needed to reach the equivalence point? So I need to know the ratio of acid to base. So I have KOH plus HNO3. So this is going to give me KNO3 plus H2O. And when that's balanced, the ratio of acid to base is going to be 1 to 1. So then when I set up the stoichiometry, I have a volume and a molarity for the KOH, but I only have a molarity of the HNO3. So that means I'm going to start with the volume of the one I know more about, which is the base. So I'm going to go ahead and change this to liters before I put it into my stoichiometry. So 0.025 liters. You can put the milliliter conversion in there if you want, of KOH. I'm going to use the molarity to get rid of liters. Then I'm going to use my mole ratio from the balanced equation to convert to moles of nitric acid. So 1 mole of HNO3 for every 1 mole of KOH. Then I'm going to use the molarity to cancel out moles. So that's 0.100 moles of HNO3 per 1 liter. And then since it wants milliliters, I'm going to do one more step here to convert to milliliters. Then I would need 25 milliliters of HNO3 to reach the equivalence point. So the other type of calculation you may have to do is it might ask you what is the molarity after the neutralization reaction occurs. It also might be stated as what is the molarity at the equivalence point, what is the molarity after the end point. So lots of different versions of how you might see the wording on this one. So again, on this one, we're going to use solution stoichiometry. We're still going to write the balanced equation to figure out our ratio. We're going to start with the volume of the substance we have more information about, so very similar to what we just did, except this time we're solving for moles of the unknown. Then we're going to divide by the volume to convert it to a molarity. So on this one, I have KOH reacting with HCl, and I want to know what is the molarity of the HCl. So this one's a little different than the other one, but I'm still going to use solution stoichiometry. Still going to start with balance equation. And this one is also 1 to 1. Be careful because they are not all 1 to 1. You always want to write out the equation to check. I'm still going to start with the volume of the one I know more about. And I'm going to go ahead and change it into liters before I put it into the equation here. 0.02070 liters of KOH. 0.5 moles of KOH per 1 liter. according to our balanced equation, 1 mole of HCl per 1 mole of KOH. And at this point, I can solve for moles. So I have 0.01035 moles of HCl. Then to change that into a molarity, I have to look and see what was the volume of HCl that I started with. So I'm going to divide this by 0.015 liters. So I just converted that milliliters to liters. And that gives me a molarity of 0.69 molar HCl. So very similar, except you stop one step early and then divide by the liters. Okay, now we can also have weak acid, strong base titrations, or weak base, strong acid. So we're going to focus on the weak acid, strong base titrations in our examples here. So if we're doing a weak acid, strong base titration and we want to calculate pH changes, we're going to use a BCA table. The difference is, since this is not strong and strong, we have to use a BCA table and we have to decide which part of the system what you're adding is going to react with. So for a weak acid, strong base equation, you're going to have the weak acid plus the OH minus, which will give you the conjugate base and water. You run it through your BCA table, and then once you have your moles at the end, you convert them back to molarity. Then you're going to use the Henderson-Hasselbalch equation to solve for the new pH. So here's an example for that one. I have 40 milliliters of 0.025 benzoic acid, and it gives me a Ka. It's titrated with 0.05 molar sodium hydroxide. So before I start this, I want to make sure I've identified what kind of reaction this is. So benzoic is a weak acid, sodium hydroxide is a strong base. So that's what's going to help me realize that this is going to be a different type of different type of BCA table than the one I'd use for strong and strong. So for this one, I'm going to start with the weak acid. So HC7H5O2. Again, this is BCA. Just as a reminder, everything has to be in moles. And then it's going to react with the OH minus. And then what that's going to generate is the C7H5O2, which is the conjugate base, and H2O. The H2O I'm going to put off to the end here because I'm not going to need that. Just like before, everything has to be converted to moles before it goes into this equation. So the first thing I have to do is figure out how many moles of benzoic acid I have. So for this one, I have 0.040 liters of 0.025 benzoic acid. So that is 0.001 moles of benzoic acid. And then I'm adding 0.010 liters, which is this 10 milliliters, of 0.05 mole per liter NaOH. So that's going to be 5 times 10 to the negative fourth. So that's my initial OH minus. And then for this one, because this is not a buffer, there's no C7H5O2 in there to start with. Okay, then just like my others, I'm going to subtract the one that's smaller from the left, add it to the right, so when I subtract that, I get 5 times 10 to the negative fourth. All of the OH minus gets used up. 5 times 10 to the negative fourth over on this side. Then before I can put it back into the Henderson-Hasselbalch equation, I need to divide by the new molarity, the new volume. So before I can put it back into the Henderson-Hasselbalch, I need to divide by the new volume. So I had 0.04 liters and 0.01 liters, which is 0.050 liters. So that gives me 0.01 molar acid, 0.01 molar conjugate base. So now I can use Henderson-Hasselbalch. The pKa for this one will be the negative log of 6.3 times 10 to the negative fifth plus log base over acid. So the pH would be 4.20. So if I'm calculating volume needed to reach the equivalence point for weak acid, strong base, the method is going to be the same as what it was for strong acid, strong base. So I'm going to use solution stoichiometry, use my balanced equation, start with the volume of the substance I have more information about. So for this one, I have a 40 milliliter sample of 0.025 benzoic acid, and it's titrated with 0.05 molar NaOH, and I want to know how many milliliters of NaOH are needed to reach the equivalence point. So before I'm going to do anything, I'm going to write out the balanced equation. So I would have sodium benzoate plus H2O. And if I balance this, these are all 1 to 1. So I'm going to start with the one I have more information about, which is the benzoic acid. I'm going to go ahead and change it to liters. I'm going to use my ratio from the balanced equation. So 1 mole of NaOH for every 1 mole of benzoic acid. Then I'm going to use the molarity of the NaOH to convert it to liters, and then convert to milliliters. So this would give me 20 milliliters of NaOH needed. The other type of problem you could do with these is calculating the molarity after a neutralization reaction. So again, this is going to be the same as what we did for strong and strong. So I need the balanced equation, which is going to be the same as, well, actually it's not. So I need the balanced equation, which I have, this time we're using acetic acid, reacting with NaOH. And again, I'm going to start with the one I have more information about. So I'm going to go ahead and convert it to liters, 0.0225 liters of NaOH. Use the molarity to convert to moles. Use the mole ratio, which is going to be 1 to 1. And again, they're not all going to be 1 to 1, so be careful with that. You always want to write out the equation just to make sure. Okay, and then this one we're going to stop at moles, so 0.00225 moles, and then divide by the volume in liters to get the molarity. So for this one I end up with 0.15 molar HCH2 H3O2. Okay, the last type of calculation that we're going to look at is solubility equilibria. So a couple different things you could be asked to do on this. So for solubility equilibria, which is KSP, you could be asked to solve for the molar solubility or the KSP, or figure out if you're going to have a precipitate form. So we're going to go through an example of each of those. So if you're solving for molar solubility, this is the best way to set these problems up. Start by setting up an ice table, and while looking at your dissociation of whatever your substance is, set up the equilibrium expression, or the KSP. Use the KSP expression to solve for X, because X is equal to the molar solubility in molarity. So if it's asking for molar solubility, basically you're solving for X if you use this method. If you're asked to solve for molar solubility in grams per liter, then you take that value that you found up here and you convert it using your molar mass. If you're asked for a concentration of a given ion, use the ice table to see how the molar solubility, or how your X's, relate to the concentration of the ions. And we'll talk a little bit about that as we go through this first example. So this one says silver chromate, Ag2CrO4, dissolves in water, gives me the KSP. What is the molar solubility of silver chromate in water? Okay, now this you have to be careful of. If it's water, that means you don't have any common ions. If they wanted the molar solubility in some other substance, you would have to pay attention to whether or not that had a common ion. So molar solubility, we're solving for X. Now these are going to be ice tables, so no more BCA tables. These are going to be ice tables, so I'm going to be using molarity when I put them into here. So the first thing I want to do is set up, what does the dissociation look like? So I'm going to get 2 Ag plus and 1 CrO4 minus 2. So that's just dissociating that. Because this is a solid, that first column is not going to change, so we're going to put lines through it. And then, like I said, the next thing I would do is go ahead and set up the KSP expression. So K expression for this is just like all the others, where you raise these to the power of the coefficients. Okay, and then I'm going to set up my ice table. So for this one, because this is in water, there's no common ion, so both those initial numbers are going to be 0. Then I'm going to add the difference using the coefficients. And I'm using x's because I don't know what the molar solubility is. So this is going to be 2x, and this is going to be plus x. This is a 2 because its coefficient is 2. This is a 1x because that coefficient is 1. So that means that equilibrium, I have 2x silver and x chromate. So then over here, I can plug those values that are at equilibrium into this expression. So the Ag was 2x, and then that's raised to the second power. And then CrO4 minus 2 is x. The KSP is given up here, so I'm going to sub that in. So that is equal to 4x squared times x. So 1.12 times 10 to the negative 12 equals 4x to the third. So you're going to divide both sides by 4, so you end up with 2.8 times 10 to the negative 13 equals x to the third. So then when you solve for x is equal to 6.54 times 10 to the negative fifth. And since this is a molar solubility, that is, you have to put a unit on it, so that would be molar. Now, if it was asking for the solubility of an individual ion, you would look at how those ions relate to the x. So if it wanted the solubility of the silver ion, you would multiply this by 2. If it wanted the solubility of the chromate ion, it would be the same as what the molar solubility of the substance is. The next type of solubility problem you could have to do is you could have to solve for KSP given ion concentrations or molar solubility concentration. So you're going to set up your ice table again, set up your expression, use the information given to figure out the concentrations of the ions, and then you substitute those ions into the KSP expression and solve. So this one says calcium fluoride dissolves in water. The molar solubility is 2.15 times 10 to the negative 4. So that is x. So molar solubility, again, we said was x. So calculate the value of the KSP for calcium fluoride. So I'm going to start this one the same way as what I did the other one. So I'm going to set up the dissociation. So Ca plus 2 plus 2F minus. This is an ice table, so these are molarities. Nothing goes in that first column because that's a solid. And then I'm going to set this up the same way with the x's. So this increases by x, this increases by 2x, so this is x, this is 2x. I'm also going to set up the KSP expression. So calcium plus 2, F minus raised to the second power. And then I'm solving for KSP, and they gave me x. So that means that calcium is equal to x. So x for this is going to be 2.15 times 10 to the negative fourth. 2x for this one is going to be 2 times 2.15 times 10 to the negative 4. So those are the values I'm going to sub in for these ions over here. So 2.15 times 10 to the negative fourth. For F, 2 times 2.15 times 10 to the negative fourth. And then don't forget, you have to raise that to the second power. Solve for that, and you end up with 3.98 times 10 to the negative 11. So that would then be your KSP. Okay, the last type of problem with the KSPs is a precipitation problem. So what these questions will ask you to do is to figure out whether or not a precipitate forms. So in order to do that, you have to have the KSP for the potential precipitate, and you have to have enough information to solve for Q for that potential precipitate. So Q is solved the same way that K is, only Q values are when they're not at equilibrium. Once you have a Q, you compare Q to K. If Q is less than K, then you will not have a precipitate and you could dissolve more solid. If Q is equal to K, then the solution is what we call saturated. If Q is greater than K, then the solution is supersaturated, and you will have a precipitate form. So it says the solution contains lead 2 nitrate and it's mixed with one that contains sodium bromide to form a solution that's 0.06 molar lead nitrate, 0.0158, and this should be molar, and NaBr. Does a precipitate form, and then it gives me a KSP for PbBr2. So this is the potential precipitate. So I'm going to go ahead and set up the KSP here. Before I do that, let's look at how this dissociates just to make sure we get the equation set up correctly. So this is going to be Pb plus 2 2Br minus. So that means the KSP is going to be Pb plus 2 times Br minus raised to the second power. Okay, now on these you have to be careful with how the information is given. This one is relatively simple because it already gives it to you in molarities. Sometimes they will give you volumes and molarities of each of these things that are mixed together. When it gives you those, you have to calculate the new molarities once the volumes are mixed before you can put them into this KSP equation. This one is a little more straightforward because they've already done that for you. So then for these, this is actually a Q calculation because this solution is not at equilibrium. So the lead concentration comes from the lead nitrate, so this is going to be 0.06. The Br minus concentration comes from the NaBr, so it's going to be 0.0158 squared. So then that gives me a Q value of 1.50 times 10 to the negative 5th. My K value is 4.67 times 10 to the negative 6th, and that would have to be given, or you would have to look that up. Now we're going to compare those two. So if I compare the Q to the K, the Q is greater. And based on my rules that I just talked about, if Q is greater than K, then a precipitate will form.